Welcome to Chemistry 112. Today we're going to continue with Chapter 20. Maybe quickly look at the learning curve. Start looking at test number 4. We're going to have that next week, most likely on Thursday. Same way we had it last time. Evening test. If you can't make it that Thursday, come find me before then. The test is written. The test is ready. The only reason I'm waiting until Thursday is to give you guys a full, as long as you can to get ready for it. So keep that in mind. Don't put it off to the last minute and then suddenly go, oh, I have something on Thursday and Friday. I have some sports thing that's taking me off campus, some Renaissance thing. I'm going to be gone. It's like, well, you've had a whole week. One other thing, keep in mind, don't be forgetting to do the online labs. Those are not just to make up. Those are not just for to make up for missed labs. Those are actually part of the score. Working on that. Quite a few people have actually turned them in, but there's some people who haven't turned in any. And I do not want to get to the end of the semester and have everyone slam me with 50 online labs. Some of them actually take a little bit of time to prep for. So keep that in mind. And last thing, real quick. The last thing is that there is a vaccination clinic over at the Velo tomorrow. Maybe sign up for that if you're interested. It's an easy chance to get Moderna. Right here, you don't have to go anywhere. It'll be right here on campus. So maybe sign up for that. Help us get back to the nearly normal so we don't have to be doing as much of this online stuff. Though I'm sure some of you like to be able to just flop out of bed and come on in. Here's what we got. We last left on last week discussing about radioactive series, the idea that some radioactive nuclei will not just undergo one decay, but multiple decays. Part of a series. Uranium will eventually decay down to lead. There'll be a lot of alpha and beta decays, but mostly alpha. Now, where we want to go with this is the next slide talks about the stability diagram, a whole idea of how do we predict what type of decays are going to happen. So just like with the electronic shell, there's certain numbers that are perfectly stable. There's certain numbers that are stable. Like we had 2 electrons fill the S, 6 electrons fill the P, 10 electrons fill the D, 14 electrons fill the F. Well, the same way, there's certain ratios of protons to neutrons that are particularly stable. Protons in a nucleus by themselves would normally want to repel each other, but neutrons help space them out so that we can hold the nucleus together. This strong nuclear force are going to bind the protons and neutrons together, and the neutrons are there to help space the protons out to reduce repulsion. Generally speaking, all atoms between number 2 and number 20 will have equal number of protons and neutrons. So if you count the carbon is 6, the molar mass is 12. Nitrogen is 7, the molar mass is 14. Oxygen is 8, it's 16. So on and so forth. That pattern holds pretty validly up to element 20. Then we start to shift away from that. We start to get more and more neutrons to help stabilize the nucleus. If you look at the book on this, they'll talk about there are certain numbers that will be particularly stable. Generally speaking, even numbers of protons, even number of neutrons, or even atomic mass will typically be more stable than things labeled odd, like an odd number of neutrons often makes a radioactive element, or an odd atomic mass will be a less stable element. So this little chart here shows the number of protons versus the number of neutrons, and how that red line is the 1-to-1 ratio. You see, after a certain point, these little blue dots start shifting away from the line as it gets heavier and heavier and heavier. Though generally speaking, the blue dot is that valley of stability, this region where the atoms are completely stable. Things that have too many protons, which would be shifted to the right here, will undergo positron emission. Remember, positron emission breaks up a proton and forms a neutron. So you'd be moving one down, one to the left and one up, help trying to get it back to that valley stability. Atoms with too many neutrons would undergo beta decay, which, remember, breaks down a neutron and makes a proton. So it moves it one down and one to the right. So the type of decay it undergoes depends on where it is in relation to this valley of stability. Every element above lead is radioactive. Lead-82 is the heaviest atom with a stable ratio of neutrons to protons. Everything heavier than lead is mildly radioactive at the very least. So bismuth, polonium, astatine, radon, francium, radium, actinium, thorium. There's uranium in there, plutonium, all of the elements there. That's not to say that any of these elements below lead aren't radioactive. It just means everything above lead, there's no stability. The valley ends. So lead is this last little thing up here. So above here, we're going to go alpha decay, which loses protons and neutrons and tries to move it back down into this valley. Once again, remember, I just said uranium will naturally decay to lead. It takes a long time, but it will decay to lead. Get to that last stable element. Now, as I said, the reason for decay, if it's above the belt, which means too many neutrons, it's going to go beta emission, which breaks down the neutrons to form protons. Below the belt, there's going to be too many protons. It's either going to be positron emission or electron capture, which essentially converts protons to neutrons. Generally speaking, the light nuclei will go positron emission. The heavy nuclei, because they will have more electrons, prefer electron capture. And everything above lead will undergo alpha decay to get back down to 82 or below. Now, we're going to talk about radioactive decay. This stuff right here is some of the same stuff we kind of briefly talked about in kinetics. This is the same general thing. On the test, it will have the same type of math, except it will specifically only be first-order decay. When a radioactive decay occurs, it's a very regular pattern. Regardless of whether this is alpha, beta, positron, electron capture, this is a very regular process. Because we're only looking at the singular atom decaying by itself, all of these guys are going to be first-order decay. There's not a second atom in it. Yes, there is a bunch of atoms, but when it undergoes a positron decay, it's coming from the individual atom is breaking apart the proton to do a positron, or the individual atom is breaking apart a neutron to do the beta, or the individual atom is ejecting an alpha. And it is not undergoing any outside forces. So that means it's first order decay. It only depends on the atom itself, which means this is going to undergo a constant time interval for a half-life. There's a predictable time interval to expect when you try to count exactly how long will it be till half the material has undergone decay. Remember, a half-life is defined as half the concentration, we half the mass, we half the whatever, however many atoms. So if a half-life is 2 years, after 2 years it goes to half a gram. Another 2 years, that half a gram goes down to a quarter of a gram. Another 2 years, and it goes down to 12.125 grams, an eighth of a gram. So that's kind of the bad part about nuclear chemistry. When you're trying to get down to zero, it's going to be an infinitely slow decrease because it may start fast and then it's going to go slower and slower and slower. Each radioactive element will have a different half-life, and so each radioactive element will take a different amount of time to decay. But one of the problems is we can't really speed this up. There's no way we can make this go faster. We can't add something here, add something there, and make this take less time. But this allows us to do some neat stuff with here. We can't really speed this up or slow this down. It's a natural rate. And since it's constant and well known, we can use this, the detection of radioactivity, to determine the age of something. This is the idea of how carbon dating works. Carbon-14 is a radioactive carbon isotope. How we get carbon-14 comes from conversion of nitrogen to carbon. So nitrogen is element 7, carbon is element 6. Nitrogen has a mass number of 14. Carbon typically has a mass number of 12. Well, cosmic ray comes in and knocks out a proton. And so suddenly, well, actually it's going to hit a proton and convert it into a neutron, thus keeping the mass as carbon-14. Now this mass at 14 as it gets converted from nitrogen to carbon. Now this carbon-14 gets incorporated into CO2. So we have heavy carbon dioxide. As we know, part of the plant's natural breathing cycle, they absorb the CO2 and incorporate that into their cells. So they're going to uptake this carbon-14 into their cells. Now, when animals eat the plants, that gets incorporated into the animal cells. And when we eat the animals, it gets incorporated into our cells. Now, here's the thing, is that the percent of carbon-14 is essentially constant throughout the universe. Well, at least constant on Earth. And as long as we're alive, and as long as we're living and eating and breathing, we're going to have a more or less constant ratio of carbon-14 within the body. Sure, it's going to be decaying, but the time period it takes to decay is much longer than the period which we're alive. So we're going to keep it more or less constant ratio based on how it is in our body, how it is in nature. So when you die, when, like, say, you cut down timber tree and make it for, I don't know, like a Viking longboat or Noah's Ark or whatever, you figure out when you're trying to radioactively date, like Dead Sea Scroll or King Tut. The idea is that when he dies, the carbon-14 is no longer being reabsorbed. So at this point, it could only go down. The half-life of carbon-14, I think it's 5,730, but it's essentially 5,700 years. That's how long it takes for half of the amount of carbon-14 to go away. With this in mind, if we know the half-life, we can measure the calculating what fraction should be and how much fraction it is. We can figure out what is the age. When did that thing die? If you find like a frozen and amber caveman, you can figure out how old must that caveman be. Frozen in ice, woolly mammoth, you figure out what time did this come from. However, because of the nature of half-life and our detection limits, objects older than 50,000 years are really hard to measure. It starts to get a little iffy because you're looking at halves of halves of halves of halves of halves of halves of halves and so on. And you're looking at such a small change at that point, you might not be able to accurately date it. You might be able to get close, but it starts to become an error. Now, the same way, we can measure the age of rocks on Earth. We find a rock somewhere in the Earth's core. Uranium will naturally decay to a special isotope of lead. Not the naturally abundant type of lead, but a heavier isotope of lead. So if we look at a radioactive rock that has still trace amounts of uranium, and we measure how much of this heavier isotope of lead, we can figure out essentially, well, this must have had this much uranium to start with, and it has this much uranium left. If we figure out those two numbers, figure the ratio, we can figure out essentially how old is this rock. Now, there's still a chance, oh, this rock is from an asteroid that slammed into the Earth so many millions of years ago, and that makes it a little bit harder to determine. But if we assume this rock was present in Earth and its formation, we can approximately calculate the age of the Earth. This rock was here in its natural state at such and such time. So, how to calculate rates of decay? Remember, a first order rate was rate equals a constant times the initial number. However, we will typically look at this as an integrated rate law, a natural log function. So we have a natural log of the concentration at time t over the concentration initial equals negative kt. So k is our rate constant, t is our time. And to do the half-life, to calculate k, we would say k equals ln2 over t1 half. So in the case of carbon, we'll take ln2 over 5,700 or 5,730, depending on the exact number. And that would give you k in years, k in inverse years. So whenever you use your time, you got to make sure you're looking at the time in years, not the time in days, not the time in seconds. So you got to make sure the units of k match up with the units of time. So a lot of these things will be dealing with years, or because most of these things will take a long time to decay, though there will be some things that will take days or weeks or some hours. Some are fast decayers, some are really, really slow. Yep. Let's look at a quick example of 500 kilogram drum of uranium-238. It's stored for 1 billion years. Billion is, so that's 10 to the, what, that's 100, that's in the 1,000, that's in the millions, 1 billion, 10 to the 9th. So how much will be left after that 1 billion years? Please note that, though, the T1 half is 4.5 times 10 to the 9th. And then how long would it take to get to 1 kilogram left? 1 kilogram. Pull up the doc cam. So we have our first thing we need to do is find out what is our K. 4.5 e to the 9 equals K. So remember, to the ln2, close the parentheses, 4.5, I'm going to use my, we'll say 4.5 divided by 10 root 9. We get a really small k. K is 1.54 10 to the negative 10th. Now, ln, we'll say n sub t over 500 equals negative k e to the negative 10th te times 1 times 10 to the 9th. First thing, find out what is negative kt. 10 root 9. You get negative 0.154 equals ln n sub t over 500. Next step, don't forget this, inverse natural log to both sides. Inverse natural log to both sides. That would give us 0.857 equals n sub t over 500. And then I would multiply both sides by 500. So how much is left after a billion years? Still 428.6 kilograms. That's how much uranium is still in that barrel. Let's look at it. How long would it take to get to 1 kilogram? 1 kilogram. So rearranging that equation, ln 1 over 500 equals negative k sub t, 0.54 e to the negative 10th times t. So let's do ln 1 over 500. That's negative 6.2146. I divide by our negative k, 54, 10 root negative 10. How many years? 1.54 e negative 10. Scroll that up. You would find out that t is equal to 4.035 times 10 to the 10th. Essentially, 40 billion years. We'd have to store that barrel 40 billion years to reduce 500 kilograms of uranium down to 1 kilogram of uranium. While I'm not going to lie and say that nuclear energy isn't a super energy, if you can figure out how to deal with some of the problems, it is a lot cleaner than, say, the polluting energies like CO that produce CO2 and sulfurs and nitrogens and all sorts of other gases. However, it does take a lot of long-term commitment. Yes, there are new technologies out there that can take some of the waste byproduct from these, the waste byproduct from these reactions and reuse them and do other things with them. However, some things we do have to store. Keep in mind, we're not typically storing uranium. We don't typically store uranium because we're going to utilize that fuel source in a nuclear reactor, which we're going to talk about in a slide or two. So we don't have to store the uranium for that long. because we're going to be storing something else. But still, most of these things still have a really, really long time lifespan. Now, this whole idea here is we can make new elements using nuclear chemistry. We're going to create pretty much how we create every heavier element. If you look at the periodic table, there's a lot of stuff that are man-made elements. They are created by speeding up like a proton or neutron or alpha particle and slamming it into a certain element. The particle accelerators like the relativistic heavy ion collider or large hadron collider will speed these up to near light speed, and they slam them into a heavy element. Now, some of the stuff can be used for medical treatment, like as cobalt-60, or there's various radioactive iodines we can form that essentially you put into the body. They get taken up in cells, typically by the cancer. Typically by whatever organ has the cancer, and then it's a naturally occurring radioactive source that can essentially pinpoint, treat the cancer. If I try to use X-rays or whatever, some of those are kind of scattershot, and that hits everything. But if you can get a radioactive isotope directly into a cancer cell, well, then you got the localized damage. But every element above 92 is generated in this method. Some of these only exist for less than a second, and we have to actually figure out they existed by the byproducts of their decay. So we form this, it goes away, it goes to something else, and we go, oh, that made a new thing, and we shut off this particle. It must have been blah. It must have been tennessine. It must have been moscovium. It must have been this, because it gets formed, it decays, and the decay pattern tells us, oh, we must have formed that. But so some of this nuclear math is the exact type of stuff you're going to be asked on the test. So don't overthink this. The whole idea is the sum of the left must equal the sum of the right. If it's a particle, you write down the particle. If it's an element, you write down the element. So I'm writing these down so we can work them out. C14. Silicon, I think that's element 14, 28. Collides with an alpha particle. 4/2 alpha. And last one, americium, 241. God, what is the atomic number for americium? Will break apart to form a gamma particle, neptunium, and something else. Let's see. Neptunium 237. Now, on the test situation, you will always be given the mass number, but you can sometimes be given the atomic number. 37, so 93. Okay. Once again, go to the doc cam. So here we have 14 plus 0 on the left. That must be equal to 14 on the right. So we have 14 here. So 14 plus x equals 14. So whatever we're releasing has the mass number of 0. The atomic number is 7 plus 0, so a total of 7. This is 6. Whatever this is must be plus 1. 6 plus 1 is equal to 7. Now we have to figure out what has an atomic number of 1, but a mass number of 0. That is a particle of beta plus. The positron emission is the particle that has plus charge but 0 mass. Now this one is more stable, easier to understand. Silicon 28 plus alpha particle 4, whatever it's going to add up to is going to be 28 plus 4 is 32. 32 on the left, 32 on the right. 14 plus 2 is going to be 16. 16 on the left, 16 on the right. Then I look at what is the particle that has 16. That is sulfur. Sulfur. We use this to determine that. Americium 241 equals blank plus 0 plus 237. So 237, 241 minus 237 is 4. 95 equals 0 plus 93. This must be 2, because 93 plus 2 is 95. Now you can either write this as alpha particle or helium atom. So americium will undergo alpha decay to form neptunium. It also releases gamma particles, but the main thing is the alpha decay. So that's what I'm saying. When nuclear math, you have to figure out either missing element with its atomic mass or what type of decay it is. But the idea is that on the left side of the arrow, all the masses add up to the right side of the arrow. On the left side of the arrow, all atomic numbers add up to the right side of the arrow. If you can add those left and right, you should be fine. You just got to make sure you have your calculator. Now, briefly talk about nuclear reactors. How do they work? Nuclear reactor essentially involves neutron bombardment. We hit a uranium atom, a special enriched uranium atom, with a neutron. This uranium-235 goes to uranium-236. This is particularly unstable. And then uranium will start to fragment into 2 different elements, either depending on how much energy and what path it takes. It will either break apart into tellurium and zirconium and 2 new neutrons, or barium and krypton and 3 new neutrons. But the idea here is that we are producing more neutrons than we started with. And so we have a cascading effect with the neutrons will produce more neutrons and produce more neutrons. And what we will talk about in a minute is that this will also produce a lot of heat. So we have to just start the reaction going so it produces some amount of neutrons. Now, this continuing to produce more neutrons is going to be a chain reaction. However, not all of these neutrons will have enough energy to continue this chain. It's not so much as the pushing the neutrons in it, but the neutron must slam into the uranium with enough force. Some of the neutrons may not have the energy. Some of the neutrons may hit the side of the container and thus just die, essentially. So we need what's called a critical mass. We need a certain amount of mass of uranium in a certain arrangement so that we can keep the reaction going. We can have at least 100% we have a 0% neutron loss. We're saying we keep it at equilibrium. For every 1 neutron used, another neutron starts the next reaction. As long as we can keep that process going, we can keep the reactor using up. Now, uranium-235 only has a 0.71% abundance in uranium. So this is not very prevalent. So oftentimes you'll have a uranium enrichment facility where they'll take really powerful centrifuges and centrifuge uranium to get to separate the uraniums by mass. So you can get this special U-235 that when we hit it with a neutron, will go into this. However, uranium-238 can be converted into plutonium, and that will be able to be used in plutonium reactors. So if we hit 238 with a neutron, after 2.3 minutes, that's the half-life, it goes to neptunium. Then it undergoes a beta decay, and a beta decay. And then it undergoes another beta decay to go to plutonium after another 2.3 days. So it doesn't take very long to generate the plutonium. Now, as we see in this diagram, I'm not sure what we have on the next slide, so I'm going to keep talking right now. But we can see right here, we have the giant steel container. We have some shielding right here, thermal shielding and biological shielding to try to prevent the radiation from leaking out and killing us all. You have the uranium bars, and we have different types of controlling bars that we can put in there. Things like carbon, graphite, or say boron. Basically, the control rods' purpose are to absorb the excess neutrons. We use them to slow down the reaction and stop it, so that if you separate the amount of uranium, it becomes subcritical and the reaction slowly peters off. However, the reaction does not instantly cease, because there's still, even if the control rods being there, does not stop the neutrons from flowing. We just have to capture more neutrons than are released. So if the neutron still hits along the rod, the neutrons could be shot up, down, left, right, front, back. The rods are just going to protect the front, back, left, right. But this rod itself can react with itself. And so the reaction will slowly have to peter out over time. Now, we also need coolant. This coolant is going to serve to get the heat away from here to prevent things from melting, but also to help get the actual energy flow. The actual energy flow must be taken to somewhere, some steam generator. Now, the first nuclear reactor was created by Enrico Fermi in Chicago, in the University of Chicago. They actually put it together as a proof of concept underneath in the squash court underneath the stadium in there. So they just had a giant pile of uranium with graphite rods, just giant bricks, and they slowly pulled out the graphite rods to see proof of concept, the whole idea that we can have a chain reaction. See, like, oh, hey, this is the first atomic pile underneath here. So very simplistic, not like a fancy reactor, but had things gone horribly, horribly wrong, University of Chicago might not be there no more. Now, there's different ways they use the fuel in the reactor. They could have, say, metallic uranium. It's just pure elemental uranium. But they could also have ceramic uranium oxide, or make uranium carbide as plates or pellets or pins, essentially assembled into a certain geometric pattern that the engineers are going to figure out this is the best way to get this energy out. Sometimes they're like coated with stainless steel or zirconium alloys to help keep the shape. Now, as I said, there's going to be a moderator. So neutron's going to slow down to ease reaction by water or heavy water, graphite, beryllium. Certain organic compounds are slowing them down so they don't have too much energy. Help make the reaction go properly. We have then control system. We have the rods that absorb the neutrons, like boron and cadmium. They're going to absorb the neutrons to stop the reaction. Now they can speed the reaction up or slow the reaction down by partially raising the rods or lowering the rods in there. They go, oh, my goodness, we're having an epic level snowstorm in Texas. We need lots of energy. Let's make the nuclear power plant produce more energy. We're going to raise the rods so they're not blocking as much and speed the reaction up. But so we need to remove the energy from the fission capture. So we're going to use things like air, helium, CO2, sometimes water, sometimes organics, sometimes even liquid sodium and liquid lithium. This is used to eventually boil the water that will run the turbines. So we essentially have a system of coolant that will heat up a separate solution of water that is in a separate container. We're going to heat up water with the coolant solution, and that water will turn into steam. The steam turns the turbines. Everything, almost all of power plants work on the same general principle. Heat up water, water goes to steam, steam turns turbines. You do that in coal fire plant, heat up water with the coal, water turns turbines. You do that with pretty much any of them, water turns turbines. Hydroelectric dam, we're just using the water falling. Water plus gravity turns turbines. But also we need radiation shielding, essentially keeping us from dying. Concrete works pretty well, steel. But you can see here like the difference up here is like, I think, the ore, and then down here is after it's been used. You can see a distinctive difference in the structure. But so most of the turbines work kind of like this. There's just various different types. Here's the rods. We have a primary loop. This is the coolant. Maybe it's sodium, maybe it's something else, maybe it's just water. But then the steam loop. The heat is exchanged when these two pipes get really close, and then it gets turned, boils the water, water goes steam, steam turns the turbine. You could do a steam line here, boiling water reactor, or sometimes 2, 3 different loops here. And those giant circular power plant, those giant circular like areas, the giant buildings that you always see in the nuclear reactors, those the thing you always associate with a nuclear reactor, those domes are just there. The giant like empty cylinders are there to cool the steam line. We're allowing them to air cool so it can go back to the water phase and boil again. That's just there so we don't have to spend any of our energy that we just gained cooling the water. We're going to let nature take its course. We just need a really big area to allow those to cool, because we're producing gratuitous amounts of heat. Now, when we talk about nuclear power, the idea, though, is we have to worry about nuclear waste. The one major problem is nuclear catastrophe. When we have a failure, it's rarely just one failure. Now, the danger is minimal in 99% of cases. But when things go bad, there's a chance they go really bad, and then you become like synonymous for this. You have 3 Mile Island, you have Chernobyl, you have Fukushima. I know Fukushima is pretty old, but we're still dealing with, still every now and then seeing the news, oh, radioactive pigs from Fukushima is traveling in Japan. I'm not sure if you remember what happened there, but essentially they got hit with an earthquake followed by a tsunami. It's a nuclear power plant in Japan that the earthquake killed the power for the thing, so they could no longer control the nuclear reactor, which is bad. But they have backup generators. Boom, backup generators running, everything's fine. What they didn't plan for is then the resulting tsunami that came after the earthquake would then flood the backup generator plant, killing those as well. So they kind of didn't couldn't stop the reaction, and I think they had some leaking of the heavy water, and so they had some issues with that. Eventually got it under control, but sometimes you don't plan for two bad things going wrong at the same time. Sometimes it gets too hot. They say your control rods jam. If they break and you can no longer control the reaction, things quickly can spiral out of control where the uranium heats so much that it then melts and turns into a slag that you can't really stop it anymore. But the other big problem is just the long-livedness of the waste. So it's a first-order reaction rate with a constant half-life. We cannot change this. To be considered to be safe, a spent fuel rod needs to undergo 10 half-lives. So if your half-life is 1 million years, you'd be looking at 10 million years before we can consider this safe. Now, there are some things we can do. We can reprocess the fuel. There's certain types of new reactors they're coming up with is they can find a way to utilize some of the waste byproducts to use them again as a fuel, kind of a recycling or upcycling that will eventually even turn them into maybe less dangerous byproducts. Either way, that means we can keep using it and we don't have to worry about it for a little bit longer. So for example, and there's other ways we can separate them and store them in separate ways. So strontium-90, for example, would only need to be stored for 288 years. Plutonium-239 would have to be stored for 240,000 years. So if we can find a way to use the plutonium byproduct, or at least separate the plutonium byproduct from the strontium, means we would be able to have one barrel that can be removed after 10 half-lives, and one barrel that would have to be will hold on for forever. But the issue is we have to think long term. We store them in a barrel, and eventually the barrel corrodes and starts to leak, and then suddenly we have a hot mess on our hands. So we have to find a way to store them for a very, very long time and not have it leak all over the place. And when has our government been really good about long-term plans? That's the one kind of issue here. Now, a nuclear bomb is just more or less a nuclear reactor that got out of control. So the whole idea of a nuclear reactor is that we have a critical mass. We have just the right amount of uranium that for every two neutrons that are formed, one neutron gets used. And so we have a net loss of, we have enough neutrons to keep the reaction going at a constant rate. With a nuclear bomb, we have a supercritical mass of uranium, meaning we have enough uranium in one place to undergo what's called a runaway reaction. So we have one neutron generates two neutrons, which generates four neutrons, which generate 8 neutrons, and it speeds up and speeds up and speeds up till it heats up, and we have essentially an explosion. Because what is an explosion? It's the rapid production of heat and the rapid expansion of gases. That's what makes an explosion. You get that shock wave of this. So you're getting heat rapidly approaching, the sun. And the gas there, if you think about the ideal gas law, the temperature suddenly goes from this to this, from 25 to 1 million. You're looking at the volume of that gas is going to expand by epic levels. And so that's what kind of causes that nuclear explosion here. Now, in order to store a bomb so it doesn't go off by itself, we store it in two subcritical sections. what we have, we drop the bomb and it hits and it launches essentially one subcritical section down here, this little red ring, into this other red ring here that fits nicely in the core. And we have a small little explosion that will kind of get it started, but two subcritical sections add together to make the supercritical mass. And then we have the big boom. I'm not sure if I've talked about this, but no, I don't. But there is also the hydrogen bomb. The whole idea of a hydrogen bomb is we're going to try to create fusion from a nuclear reactor, from a nuclear bomb. And we're going to try to fuse hydrogen together to kind of create a miniature star. But we still have to use a small amount of nuclear energy to jumpstart that reaction. So it's the hydrogen bomb actually started with, we dropped bomb, it harnesses this re-explosion, focuses all the energy into the hydrogen, and the hydrogen then starts to fuse and that produces a ton of energy, which further makes a big explosion in itself. One of the last things we'll talk about is fusion and the energy of that. And that is like what happens within a star. The main elements within a star is hydrogen and helium. We're going to burn all the hydrogen first, but essentially all elements come from this. All elements come from this fusion process. Now, there are some other processes that produce other elements, but it starts with here. That the idea is that first, helium atoms get fused together. And they form a deuterium atom and a positron emission. So it's undergoing this. These deuteriums can then fuse into hydrogen, fuse with another hydrogen atom and produce helium-3. As we generate more and more helium-3s, they can fuse together to form a natural helium atom and two more hydrogen atoms to continue the process. Or this helium-3 could undergo would confuse with another hydrogen atom to form a standard helium and a positron emission. But all this is undergoing the sun. So long as we have hydrogen, it's going to keep doing this. The first reaction produces 89 billion joules. 89 billion joules, almost 90 billion joules alone. However, to make this process work, we need incredibly high temperatures. So 4 times 10 to the 7th Kelvin, what's that, like 40,000 Kelvin, and intense pressures. However, got to remember the surface gravity of the sun is, we deal with 9.8 meters per second squared. The surface gravity of the sun is 274 meters per second squared. And that only increases as we approach the center. So we're going to have very high pressures in there, high level of gravity. Of course, once all the hydrogen will get used up, then we're going to start to react the helium. The helium can start to go fusion processes and form things like beryllium. And the beryllium can fuse to form carbon. And the carbon can fuse with helium to form oxygen. And so on and so forth. This fusion reactions will produce all of the elements on the periodic table up until we get to iron. Iron, as we'll see in another slide or so, is the most stable element per nucleon. It's the perfect ratio of energy per nucleon. And so this produces a seed element, which will create a series of slow and rapid neutron captures that will form all the heavier elements. So things when the star kind of dies and forms supernovas and all that sort of thing, that's how we produce everything heavier than iron. So we start to get more and more rare elements past iron, because you basically need the sun to go supernova and explode and shoot these elements out that they can then be incorporated into planets. All these elements come when the star kind of explodes. And so now the first law of thermodynamics has to apply here. It still applies. The energy is neither created nor destroyed. So if matter is conserved, how do these reactions generate energy? Because you got to remember, if we say, oh, hydrogen plus hydrogen equals a deuterium and a positron, it looks the masses on the left equal the masses on the right. So where's the energy coming from? The energy is calculated through our friend E equals mc squared. That energy is equal to mass times the speed of light, constant. So what is the mass? Well, the idea here is when a nuclear reaction occurs, we lose a tiny little bit of mass as energy. The actual mass of the radioactive elements are not equal to the sum of the mass of the decay products. Because if you figure the actual mass and not just the average number, they do not perfectly add up. This is the mass defect. This is actually coming from that strong nuclear binding energy is being converted into this mass loss. That strong nuclear binding energy is the source of our energy here. To calculate this, which, mind you, you will not have to do for the homework, I don't think so, and you will not have to do this for the test. But to calculate this, you must look at the exact mass in AMU, not the isotopic mixture. Because we're only going to deal with one isotope when it's analyzed. But we're going to subtract the product, the sum of the products minus the sum of the reactants to find what is the mass defect. So let's just look at uranium decay. Uranium-238 goes to thorium and helium. Uranium-238 is 238.0003. Thorium-234 is 233.9942. And an alpha particle is 4.0015. You add thorium and the alpha together, you're going to get one mass, and you're going to get what, like 237.9957. And you notice 237 is slightly lower than 238.0003. So when you subtract those two, you get the mass defect is approximately 0.00046 grams per mole. And because joules are in kilograms per meter squared, second squared, we would turn that into kilojoules, or the kilograms, and then multiply by the speed of light squared. So we would get the energy produced when this uranium decays is about 4.1 times 10 to the 11th joules per mole. That's got to remember, it's per mole of uranium. A mole of uranium would be what, like, as I said, it's 238, so it's like 238 grams. But still, that is, God, that's like 410 billion joules. Pretty big. Now, please note the exact mass is not the same as the mass in the periodic table in your book. So had we actually needed this for the test, I would have to give you those exact masses. But we're not going to have to really worry about this. We'll go ahead and calculate this. I'll skip through this since we don't actually need to do this. So how much energy is produced? Here's a mass, here's a mass, here's a mass, and you say, here's the average neutron mass. So you'd say the left side is the neutron plus 235. The tellurium is those two numbers plus 2 neutrons. So the step one would be you find the mass defect. The mass defect is this many grams per mole. 0.9198, blah, 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 blah. You turn it into kilograms, multiplied by the speed of light, you'd get that the energy produced by a nuclear bomb is on average 17 trillion, almost 18 trillion joules per mole of uranium. 17 trillion joules per mole of uranium, which is why you have such a big explosion. Such a big explosion for such a little thing. That's how much energy is released. If you can calculate that in gratuitous amounts of tons and tons of TNT, how much energy would those same amount of 1 mole of TNT produce? It's just nothing compared. Last little bit is like what all decay, what happens when a star dies. Essentially, as I said, we're looking at the mass defect is due to a strong nuclear force that has to do with the nuclear binding energy. All elements below iron right now have slightly lower nuclear binding energy. Right here is iron. So all elements below iron will undergo fusion to try to eventually get to iron. All elements above iron will typically undergo fission process, eventually trying to get closer to iron. Notice some of these are pretty high up there, so they may stop a little prematurely. But nuclear iron has the highest binding energy per nucleon, so it's usually the end product of many reactions. But I'm not going to pretend to know and fully understand what goes on in the supernova process. I look it up every year. It's still very confusing, but essentially you have a bunch of neutrons are going to hit in a bombard, and we're going to undergo a lot of fragmentations and basically produce a lot of the heavy rare metals. Now, going to achieve, there is a learning curve for this chapter. Not very much. It's over 2 topics, radioactive decay and rates of radioactive decay. So I don't really even have you do too much. So the whole idea is, which of the nuclear symbols could be used to represent an alpha particle? Given the decay rate for 1 gram of molybdenum 88, how long would it take to decay to 0.8 grams? So this one you could look at the chart. Okay. See, I can't really read that as I'm assuming that's 100%. So if you're going to 0.8, it'd be like 80%. I'm not sure where that's at. Can't really read that. It's too small. Let's see. Oh, let's see if I can do this. Okay, there. That might work. Well, I'm gonna go with 4 minutes. I don't know. I could be wrong. It's not a big deal. Not a big deal. I don't really care. But you can no. I'll try 2 minutes. Too small for me to really read. But as I said, I just want to show you what type of problems they have. Blah. Okay. So actinium is an alpha particle emitting therapeutic radionuclide targeted cancer therapies. It decays cascade product 4 net alpha particles. Identify the daughter isotope produced after the first alpha decay. So you just be like, oh, you're looking at what type of math you're looking at. So actinium 89, 225. When it undergoes alpha decay, it's losing 2 protons, 2 neutrons. So total of 4 mass to 221, and then 2 protons to 87. So we're just asking you to, I'm asking you to just think about this stuff. It's more half-life stuff. All this pretty straightforward. So that's all I'm asking for this last chapter. Keep in mind, you still have to be working on the electrochemistry and all that. But so for this chapter, as a quick reminder, what are we doing on the test? We're doing maybe some nuclear math, and when it comes to transmutation and other decay rates, and maybe a quick review of kinetics, especially with first order kinetics and the natural log. So we're almost done. We will just briefly look at this test. I don't think we're going to really get into it right now. We'll probably go ahead and get into it on Thursday. But this one was a take home. So obviously it's not going to be exactly the same, but we can still look at this. So this one I gave, this one will be a little bit harder because we have to look up you'll have to look up the source of the H, S, G, and E values. On our actual test, we'll have a source. We'll state the source. This one, you'd have to look it up and state the source so I know, like, oh, if your number disagrees with mine, I can go, oh, but he did the math right because the math matches up. So look at this. For example, there's a balance this equation. Using the overall balance equation, determine the Gibbs free energy. Okay, let's get over to you. For God's sake. Oh, come on. Gibbs free energy. Using your overall balance equation, Gibbs free energy. Determine the cell potential. Hint, you can use your Gibbs free energy. Determine the equilibrium constant. For that, you can also use the Gibbs for that. Then, okay, using the dissolution of silver chloride into silver plus and chloride minus. Determine the Gibbs energy at this. Is there a temperature where the sign of Gibbs will change? If so, at which temperature? So you're looking at like, oh, if I have delta H and delta S, looking at the entropy and enthalpy of this guy, there might be a sign where if both numbers are positive or both numbers are negative, there's going to be a temperature which that occurs. And then determine the entropy change for the universe at a different temperature, determine the Gibbs free energy at 150, a different temperature, and determine the equilibrium constant K at that 150 degrees. Describe the second law of thermodynamics, battery problem here. Determine the cell potential of the battery at 25 degrees. So we have to run that, calculating the charging potential. This is a electroplating thing. Then non-spontaneous reactions, a combustion equation. Like say, determine the enthalpy of this reaction. Without calculating, would you expect the entropy of this reaction to be positive or negative? That has to do with looking at how many moles of gas do we have on the left versus the right. Sublimation, we're looking at above which temperature will a lot of this comes down to finding the Gibbs, finding the delta H, finding the delta S. I'll show you all the equations we'll need. Predicting an oxidizing agent. Let's see, cell potential. And at the concentration, this one is the E non-standard. E non-standard. And an easy bonus. But quick reminder, here was the equations we needed for at least the last two chapters. But we'll look at this more in depth on Thursday. In the meantime, we'll just keep this in mind. This is posted on Google Classroom. So I want to thank you for your time. I will see you guys in lab, and maybe go get your vaccinations if you can.